To record to the cloud. Okay, so let's resume with our discussion of assigning configuration. So multiple bonded atoms. So multiple bonded atoms are equivalent to the same number of single bonded atoms. So whenever I see a structure, I always like to redraw my multi-bonded atoms as single bonded atoms. So this double bond is equivalent to 2 single bonds to an oxygen from the perspective of the Kohn-Ingold prelog system. Okay, so looking at this structure, what is our highest priority group? So first and foremost, we have a 4-way tie between all of our carbons, right? So now we have to draw out the substituents attached to our carbons. So my question to all of you is, what is the highest priority group? A, B, C, or D? Which carbon gets the highest? Which carbon gets the 1? Which carbon gets the lowest priority number? Or essentially, which carbon do we put the 1 next to? What's our highest priority group? Carbon A, B, C, or D? I see a lot of people saying A, so A is correct. Yep, because on our list of atoms attached, we have an oxygen, and a hydrogen. Let's make a list for all of our carbons. So for B, we have a carbon, a hydrogen, a hydrogen. For C, we have a carbon, a hydrogen, and a hydrogen. Okay. For D, we have a carbon, a hydrogen, and a hydrogen. Okay, so now let's do a tiebreaker. For B and C, we're gonna have to look 1 carbon over. Okay, so for C, we have a carbon, a hydrogen, and a hydrogen. And for B, to complete our tiebreaker, we have a carbon, we have a carbon and 3 hydrogens. So C wins out. So C gets our priority 2, B gets priority 3, D gets priority 4. Does this logic make sense to everyone? Does this counting method make sense to everyone? Okay. So I'm going to clear up some space now. And eventually you're going to be able just to assign priority of groups by site. But if when in doubt, you can make the table. So let's convert this structure into, let's convert all our double and triple bonds into single bonds. Okay, so remember a triple bond is equivalent to 3 bonded carbon atoms, right? So I drew out my triple bond to more accurately reflect how it's counted in the Kohn-Ingold prelog system. Okay, so now let's identify. So looking at our central chiral center, what is the highest priority group? What's the highest priority group? What is the highest atomic number atom attached to our chiral carbon? Oxygen, yep, exactly right. So we put a number 1. Okay, so let's keep going now. Let's keep going. So we're now going to look. So looking at our 2 adjacent carbons, it's a tie between these 2 carbons. So I'll call them A and B. So let's make a primary list. So attached to A primary, we have 4 carbons. Attached to B primary, we have 4 carbons. Okay, now we have to go further down the chain. So for our second list for A, we have attached 4 carbons to this carbon A. And then to B, we have, unfortunately, a carbon and 3 hydrogens. So which carbon is the highest priority, A or B? Which one is the highest priority using this counting method? A. So we assign A as number 2, B as number 3, and hydrogen as number 4. If you're having trouble assigning priority numbers, you're going to have some trouble with the later part. So we really want to make sure we're solid on assigning priority numbers. Any questions so far? Any questions so far? If not, let's keep going. So, step 1, we focused on it a lot. We assign priority to each group in order of increasing atomic number. Now, the next step is you're going to rotate your molecule so the lowest priority group is in the back, pointing into the page. And to this, I'm going to have to make a model to really help drive home this point. So we're going to look at some common, Jordan, do you have a question that I can address? Oh, okay. Okay, so here we go. In terms of our key, so we're looking at this from a side-on view. The bromine is going to be purple and the chlorine is going to be blue. So I'd like you to tell me which group is pointing out towards you. Which group is pointing out towards you in this current model? What group is pointing out towards you? What group is pointing towards you? Hydrogen, yep, exactly right. So what we're going to do is we're going to rotate this molecule so the hydrogen is pointing away from you. So the hydrogen is pointing away from you. So our first step, what we're going to do is we're going to tilt this molecule and we're going to bring our chlorine up top. So we're going to tilt the molecule like this to bring the chlorine up. Let me adjust the view. So we're going to tilt the molecule by rotating our hydrogen, our chlorine, and our bromine counterclockwise. So now our chlorine is on top. Our hydrogen is still in the front, and our oxygen's in the back. So does everyone see how we have chlorine and bromine making this right angle and how our hydrogen's in the front? Can everyone see how from rotation we obtained this structure? So just to show you this once again. So we started off with the following arrangement. We rotated our 3 substituents clockwise. And now as we can see, we have hydrogen in the front, the hydroxy group in the back, and our chlorine and bromine are in the plane of the page pointing right. Now we want our hydrogen to be in the back. So we're going to rotate this molecule so our hydrogen is in the back. Now what atom is pointing out towards you? What atom is pointing out towards us when hydrogen is in the back? Yep, exactly right. There we go. Perfect. So this is our final structure as drawn just by staring at the model kit. I want you to be able to visualize these rotations. So now we have hydrogen in the back and we're done with this step. Let's do the enantiomer. Let's do the enantiomer now. So I'm going to swap the position of 2 substituents. That's the classic way of making an enantiomer. Okay, so now in our enantiomer, which is down below right here, which atom is pointing out towards you? What atom is pointing out towards you? What atom is pointing out of the page? Yep, the hydroxy group, or the oxygen atom. So just like before, we're going to rotate. Do we need to rotate this molecule? Do we need to do anything special to this molecule? Or can we just draw it as we see it? So if we want to bring our chlorine on top, so to have a direct comparison, all we do is we rotate it counterclockwise. There we go. Now we have our chlorine on top, our bromine to the right, our OH pointing out, and our hydrogen in the back. And we just draw it like we see it. Does that make sense to everyone? Now, you don't have to rotate things exactly as I do. As long as you end up for where the hydrogen is pointing away from you, you've done a good job. The exact arrangement of these three substituents can change depending on how you rotate your molecule. So don't worry too much about it. As long as the hydrogen's in the back, you're good to go. Okay. So now what we're going to do is we're going to take a look at another set. We're going to take a look at another set of atoms. So in this case, we're going to look at a side-on view. So in this case, so we're looking at the following molecule here. I'd like you just to know that the purple is the sulfur and the blue is the fluorine. Okay? So let's follow this together. So we have our oxygen pointing out. Is our hydrogen in the back currently? Is our hydrogen in the back? Is our hydrogen in the back? No, it's not. So what we're going to do is we're going to bring this sulfur up like so. Okay. So we haven't gotten too far here, but now is our hydrogen in the back? Is our hydrogen now in the back? All we did was we started off with our hydrogen up top. We brought our sulfur up. Now our hydrogen's in the back, and let's draw what we see. So looking at this side, what side is our OH on? Is it on the left or the right? Our right, my left. So I'm going to draw my OH on my left. The sulfur is up top, the fluorine is on my right, and the hydrogen's in the back. Perfect. Let's look at the enantiomer. The reason why we're doing this rotational practice is these are all the common ways that stereocenters are drawn, and I'm trying to show everyone how to tackle all the stereocenters and draw them properly. So let's look at the alternate side-on view. So this is an enantiomer that's drawn as the horizontal mirror image. So here we go. Does everyone notice the subtle difference here? So even though the OH is in front, is our sulfur on the same side? Is our sulfur on the same side as our original example? Did the sulfur switch sides? Yes. So this is an enantiomer because the skeleton is drawn as a mirror image while the stereocenter stays the same. Exactly. So let's try to rotate it so this OH is in the back. So all we have to do is bring our hydrogen to the back. So all we have to do is just tilt our molecule so the hydrogen ends up in the back. So we started off with the hydrogen in the front. We bring our OH to the top. And now our hydrogen ends up in the back. And now we just draw what we see. So I see my OH is up top, my fluorine's on the right, and what group is pointing out of the page? What group is pointing out of the page in this case? What group's pointing out of the page? Sulfur, exactly right. There we go. Perfect. So let's do some more practice. And let's talk a little bit about priority groups. So this is the final depiction of your structure that you'll need for us to assign configurations. So what we're leading up to, these are all the steps necessary to assign configurations. And in the standard method for assigning configuration, your hydrogen is in the back. This is just the standard method for assigning configurations for centers. So we need to rotate our molecules so the hydrogens are in the back for all of our stereocenters. Don't worry, we're leading up to it. So we have our two steps. We assign priority, we rotate our molecules so the lowest priority group's in the back. Now, enantiomers are pairs of molecules that are non-superimposable mirror images. And enantiomers have the opposite configuration at every chiral center. So let's do one more rotational study. So in this case, our bromine would be the purple in our model kit, and the chlorine would be our blue. Okay, so here we go. Now, what we want to do, we want to end up so where our hydrogen is in the back. So currently our hydrogen is in the back, but let's try to get a little bit better view with our hydrogen in the back. So what we're going to do is we're going to bring, so we started off with our view like so. And what we're going to do is we're going to bring our bromine up top. So we started off with this, and all we did was tilt it so our bromine's up top. Now we just draw what we see. So our bromine's on top, our chlorine's on the right, our OH is pointing out. So here's one enantiomer. And I'd like you just to compare the position of our groups when we look at our second enantiomer. So I'm going to swap my substituents. So now what group do we have pointing out to us in this enantiomer? What group do we have pointing out of the page? What group is pointing out of the page? I see a lot of people typing hydrogen. Okay, so now we're going to rotate this molecule so our hydrogen's in the back. So we're going to bring our bromine up top. Okay, and now what we're going to do is we're going to rotate all of our substituents counterclockwise so our hydrogen's in the back. So now all we have to do is draw what we see. So this is another depiction that we can draw. So in this case, we have our bromine up top. We have our chlorine on our left. Well, let's think about the chlorine for a moment. We have our OH on our right. Our hydrogen is in the back. And what group is pointing out of the page in this case? What group is pointing out of the page towards us in this depiction? Yep. The chlorine, exactly right. So does everyone notice how in these two enantiomers, the group that is pointing out of the page is different? And the relative position of our substituents are different? Does everyone notice how our two enantiomers look quite different in terms of 3D shape? Okay. Perfect. So, to complete this idea, let's look at our two enantiomers once again, and let's talk about how do we assign priority numbers. So first things first, we assign priority to each group in order of increasing atomic number. Wonderful. We rotate our molecule so the lowest priority group is in the back. We've done that. Next, you're going to place the three remaining groups in a plane, just flat. You're going to draw a circle moving from, so let's rephrase. So you're going to move from the highest priority group to the lowest priority group. So the highest priority group corresponds to the lowest number, and the lowest priority group corresponds to the highest number. Okay, If your rotation is clockwise, you designate the R configuration. If your rotation is counterclockwise, it's designated the S configuration. So let's do an example. Let's look at an example. So in this case, assigning priority, bromines 1, chlorines 2, oxygens 3. So if we draw an arrow, going from our highest priority to our lowest priority group, as we see, is the arrow going clockwise or counterclockwise in our first example? Is our arrow counting from 1, 2 to 3 going clockwise or counterclockwise? Clockwise, yep. So it's clockwise, ergo we assign the stereocenter as R. Looking at our second example, at our enantiomer, so this is our enantiomer, it has the opposite configuration at every chiral center, so bromines 1, chlorines 2, oxygens 3. So if we draw out from 1 to 2 to 3, are we going clockwise or counterclockwise in our enantiomer? Yep. Yep, exactly right. So we're going counterclockwise. So we assign this stereocenter as S. Exactly right. Perfect. Does that logic make sense? When you have a set of enantiomers, one way to check your work is that enantiomers have opposite configurations at all centers. Not too bad once you break it into pieces. So let's do another example. Let's do another example from scratch. So we're asked to assign the configuration RS for each chiral center. So let's make a model. I may seem like a broken record at this point, but if you make your model, you will save yourself a lot of grief. So there's really no reason not to. So let's make a model and let's just rotate our molecule. Okay, so you need to make sure your skeleton is drawn exactly the same way your structure is drawn. So does everyone notice how the skeleton for this molecule exactly matches the skeleton in my initial picture? Okay, so my question to you is our bromine currently pointing out? Is our bromine currently pointing out of the page? Yep. Is our hydrogen in the back? Is our lowest priority group in the back? Yes. Okay. So what we're going to do is we're going to focus on just our high priority groups. Okay. Now let's assign priority numbers. Let's assign priority numbers. Hydrogen's easy because it's always going to be the lowest priority. Bromine gets a 1. What is the next highest priority group? If we had to pick between B and C, which group gets the next highest priority number? What group? Yep, the ethylene, exactly right. Does that make sense to everyone? Does everyone understand why B gets priority number 2? Okay, perfect. C gets priority number 3. We then draw an arrow going from highest to lowest priority. And are we going clockwise or counterclockwise? And let's get a few more responses. Yep, counterclockwise. So then do we assign this as R or S? S, exactly right. Perfect. Not too bad. So let's have you try to work on an example. Let's have you try to work on an example. I'd like you to assign the configuration for each chiral center. And remember, I showed you how to rotate all of the different depictions of these molecules because you're going to have to use that rotational logic to solve these problems. So I'll give you a few minutes to work on that, and I'll be making a model in the meantime to help everyone visualize what's going on. So in chat, you're more than welcome to type your proposed configuration assignment for the following molecule. Okay, I already see a few people providing their assignments. Let's get a few more responses in the chat before we talk a little bit about this. Anyone else have a guess or have a proposed solution for the following molecule? Okay, so let's talk a little bit about this. So currently hydrogen is pointing out of the page. Hydrogen's always our lowest priority group. So we're going to take our entire molecule and we're going to flip it 180 degrees. So now is hydrogen in the back? Now is hydrogen in the back? Yes. Okay, so let's draw what we see. Oh, whoops, one. So let's draw what we see in our picture. Let's draw what we see in our picture. And the reason why I'm referring so much to the screen is because from my view, I'm staring at the structure from behind. It's really unfortunate the Zoom cameras flips everything. Okay, so now we have all of our groups set up. Now we're going to focus and place our groups into a plane. So if we assign priority numbers, A, B, C, which group, which functionality gets the highest priority, A, B, or C? Which one gets the priority number 1? Which group gets priority number 1? And let's be really careful about this. I'll give you a hint. This is an amino acid. The amine gets priority 1 because we're comparing nitrogen versus carbon, and nitrogen wins out. Does that make sense to everyone? Remember, we're always focusing on the atom directly attached to the chiral center. Now, if we had to pick which atom, B or C, gets priority number 2, which one is higher priority? A or B, sorry. A or B, which one do we assign as priority number 2? So we're comparing 2 carbon atoms and thinking about what's attached. I see a lot of people typing A. Yep, that's exactly right. So we have 1, 2, 3. We're now going to draw a circle counting from highest to lowest priority. Okay. And are we going clockwise or counterclockwise? Yep. So it's counterclockwise. So what configuration do we assign? S. Exactly right. So let's go through that one more time. Let's go through that one more time just to check our work, just to check our work. So let's go through this one more time just to check our work. Oh, we deleted a methylene group accidentally. Okay, so let's start with our initial view of our molecule. Let's start with our initial view of our molecule. So this is our initial view. Our hydrogen is pointing out of the page. We flip our entire molecule over, and there are many ways of doing this. There are many ways of doing this. I decided to just flip it 180 degrees to make my life a little bit easier. And now we have to set our hydrogen pointing away from us. So in the following view, our hydrogen is pointing away from us, and we have our three groups arranged where our amine is on the bottom, our carboxylic acid is on the right, and our aromatic ring is on the left. We then assign our priority groups. The amine gets the highest priority, the carboxylic acid gets the second highest priority, and this benzyl group gets the third highest priority. Drawing out from highest to lowest priority, we're counterclockwise, so it's the S configuration. Does that make sense to everyone? Is everyone comfortable with that logic? Okay, perfect. Let's do another example. Let's do another example. So I'd like you to identify each chiral center and assign the configuration at each chiral center. So take a moment to work on that, and then we'll come together as a group to discuss in a few minutes. And you're more than welcome to type in chat, let's say A, B, when you're describing the chiral center configuration, tell me the configuration of A and B. And I'm making a model of both of these because, again, I always believe in this idea that seeing is believing. And let's try to get a few responses in chat, and then we'll come together as a group to discuss. Oh, for Carter, which center are you assigning, A or B? Okay, no problem at all. So I see a lot of reasonable answers. So let's talk a little bit about this. So here is our depiction. Here's our depiction of the following molecule. Don't worry as much about the aromatic ring. Just focus on the fact the OH and the methyl group are out, and our hydrogen is in the back in both of these cases. So we don't have to do too much rotational work. Really making life easy for you. So let's start with our first center. So we have the OH. Okay, so let's focus on center number 1, and let's draw out center number 2 as well. So for our first center, so A, B, C. So what gets the highest priority number, A, B, or C? Which atom has the highest atomic number? Which atom has the largest atomic number? A, yep. So we'll assign number 1 for A. Okay, which group gets priority number 2, B or C? Which one gets priority number 2, B or C? B, exactly right. And then C by default gets priority 3 since it's not hydrogen. So if we trace from priority 1 to priority 3, we see it's clockwise. Ergo, we assign this stereocenter as R. Does that make sense so far? Is everyone comfortable with that so far? Okay, let's focus on our next stereocenter. So, ignoring hydrogen, because hydrogen's in the back, which group gets the highest priority, A, B, or C? Which group gets the highest priority, A, B, or C? A, yep, that's exactly right. What gets the next highest priority? B, exactly right. Wonderful. Okay, and C gets priority 3 as default. We then trace a line from priority 1 all the way to priority 3, and we see we're going counterclockwise. So we'd assign this stereocenter as S. A is priority 1, not because it's an amino acid, but because nitrogen beats out carbon, right? We always assign the highest priority to the atom directly attached to the chiral center with the highest atomic number. Does that make sense? Okay, perfect. So let's keep going with a few more examples. So in this case, I'd like you to identify each chiral center and then assign the configuration at each chiral center. And we'll resume, and don't be shy to type your answers in chat, and I'll be taking a look at chat periodically to check to see how everyone's doing. And this one is a bit of a pain to make a model of, but I'll make a model just so that way everyone can see what's going on. And let's try to write our assignments for centers A and B in the chat. Everyone's quiet. Is everyone doing okay on this problem? I'm seeing some reasonable answers so far. Let's get a few more responses in the chat before we talk about this. Okay, so let's just take a look briefly at the model. Let's start at Stereocenter A, and let's really focus on Stereocenter A for a moment. So focusing on Stereocenter A, it's important now that we assign priority. So I'm gonna rewrite Stereocenter A so all of the atoms are depicted according to how they're viewed in the standard IUPAC method for assigning priority. So what's the highest priority group directly attached to carbon A? What's the highest priority group? So chlorine, so A, B, C, D. Which group gets the priority 1? A, B, C, or D? Which one? Which substituent has the highest atomic mass directly attached to our chiral center? A, B, C, or D? Directly attached to our chiral center. I see a lot of people typing B. Good. Everyone quickly noticed that we're not comparing chlorine and bromine. We're comparing chlorine and carbon. You always want to make sure you compare at the first atom attached to your chiral center, and then you move out if there's a tie. Okay, wonderful. So which group gets priority 2? B, C, or D? Which group gets priority 2? Which group is second in priority? Yep, a lot of people typing B. Bromine wins over chlorine. Okay, group D gets priority 3 and group C gets priority 4. So we need to rotate our molecule so C is in the back. Okay, so to do that quite simply, just like we did in our simplified model, all we do is we turn our model. So now this big bulky group C is in the back, and we draw what we see. We draw what we see. So our group with the bromines on top, what group is pointing out of the page? What group is pointing out of the page right now? What group is pointing out of the page towards you? Out of the page, like which group is pointing directly at you right now? Yep, it's this alkyne fragment. Okay, continuing on with this idea, and then pointing on the right-hand side is our chlorine. Okay, perfect. So we just draw what we see, then we assign our priority numbers. Once again, we remember chlorine is priority 1, this alkyl bromide's priority 2, and this vinyl chloride's priority 3. We then draw an arrow going from priority 1 to priority 3. Oh, whoops, one moment. Let me reopen OneNote. Sorry about that, mild technical hiccup. So 1, 2, and 3. And my question to all of you, is this stereocenter R or S? Looking at this arrangement of our substituents, is it R or S? See a lot of people typing S, that's right. This is counterclockwise. Ergo, we'd assign the center as S. Okay, let's take a look at our second stereocenter. Let's take a look at our second stereocenter. So I'm going to draw the simplified form. So let's take a look at it from the perspective of our model kit. So let's take a look at this second stereocenter from the perspective of our model kit. Okay, so currently our hydrogen is going out of the page. We want our hydrogen to be going into the page. So all we do is we rotate our substituents, and now our hydrogen is into the page, and we just draw what we see. We just draw what we see after rotation. So I'm going to label this group R. We have our bromine. So the R group is going out towards us. We have our alkyl chloride on the right, and we have our hydrogen in the back. Does everyone understand, after viewing that model rotation, how we obtained the following structure after rotation, how we rotated our molecule? Does everyone understand that rotation? Let me show it to you one more time. Okay, so initially, our bromine is going into the page. So our bromine's going into the page, our alkyl chloride's pointing up to the right, and our alkyl group is pointing up and to the left. We just rotate our substituents, and then we draw what we see now that our hydrogen's in the back. Okay, so let's now assign some priority numbers. Let's assign some priority numbers. So bromine is priority 1. Now comparing B and C, so which we'll just we'll draw out C as just this long alkyl chain. What is higher priority, B or C? The alkyl chain or the alkyl chloride? Which one is higher priority, B or C? B, yep. Okay, now we draw an arrow going from highest to lowest priority. And as we see, we're going clockwise. So we'd assign the center as R. Does that make sense to everyone? Does that make sense so far? Is everyone comfortable with this example so far? Okay. So let's do a more challenging problem. So let's identify each chiral center and assign the configuration at each chiral center. So let's look at A, B, and C. And let's assign the configuration at each of these centers. And I'll make a model. So it'll take me a few minutes. I'll make a model of this so that way we can study it together. If anyone recognizes this molecule, and if you've taken your biology classes and were paying attention, you may have noticed something pretty interesting about this molecule. It has a pretty unique name. And don't be shy if this takes you a few minutes. The point of this class is for us to tackle some difficult examples. If the examples all took less than 5 minutes, then I don't know how much we'd really be getting out of it. So does anyone have any proposals yet for the configuration at any of these centers? It's okay. We'll discuss in a few minutes. I know it takes a while to make the model, but don't worry, it pays off. This is a good example because it's exactly the kind of example that you'd expect to see on a challenging homework question or a challenging test question. Anyone have a name for this compound for me? This one's pretty famous. Pretty famous. Well, I'll give everyone a few more minutes. I want to make sure that you're able to pose reasonable solutions for these. Anyone have any proposals for the assignment? Anyone want to assign a configuration for any of the 3 centers? Okay, I see people already starting to assign the first center. Let's assign the rest of them and then we'll discuss as a class. Anyone have a proposal for center C? No problem, no problem. I know this one takes a little bit of time. Okay, I have a full slate of answers for each of these. So let's talk about each of them individually. So here's what this molecule looks like in a model. Don't worry about this long chain group. It's not really that relevant for assigning R versus S. Did I make the enantiomer on accident? Nope, nope. Okay, perfect. Okay, for anyone who's wondering, the name of this molecule is biotin. Pretty critical in biological systems. Okay, beyond that, let's take a look at center A. So all we have to do is rotate our molecule. So this hydrogen is in the back. So we're just going to rotate our molecule. So the hydrogen is in the back. And then we're going to draw what we see. We're going to draw what we see. So I have our sulfur on top. 1, 2, 3, 4. We have our long chain carboxylic acid on the right, and then on the left, we have the rest of our ring that I'm just going to write as R. So in terms of priority, which group gets the highest priority? Which group gets the highest priority? A, B, or C? Which group gets the highest priority? A, B, or C? Which atom, which group has an atom directly attached to our chiral center with the largest atomic mass? So you see a lot of people typing. Oh, I'm not asking for the configuration yet. Just the which. Oh, sulfur. Yep, I see what you're saying. Yep. The sulfur gets priority 1. Yep, exactly right. Which group gets priority number 2? Our amine or our carboxylic acid chain? Which group gets priority 2? C or B? I see a lot of people typing C. Yep, that's exactly right. The nitrogen has higher priority than carbon. So B gets priority 3. We then draw our arrow from highest priority to lowest priority. And as we see, it's moving counterclockwise. So then we assign stereocenter A as an S. Okay, let's take a look at center B. Let's take a look at center B. So center B is right here in our model kit. So we need to adjust our molecule and rotate our molecule so this hydrogen is in the back. So let's do just that. So we rotate our molecule so the hydrogen is in the back, and then all we have to do is draw what we see. Okay, now this is a really interesting case of assigning priority very, very carefully. Okay, so my question to all of you is, if we forget about the hydrogen since it's in the back, A, B, C, which of these groups is highest priority? A, B, or C? Which of these groups is highest priority? Let's get a few more responses. I see a lot of people typing B. That's exactly right. So B gets priority 1. Nitrogen beats out everything else. Which group gets priority 2, A or C? So if we count one atom out, attached to the atom, one atom out, which group is higher priority, A or C? C, yep, exactly right. So that gets number 2. A gets number 3. So if we draw an arrow going from our highest to our lowest priority group, my question to all of you, are we moving clockwise or counterclockwise? Exactly right, we're moving counterclockwise. Now, we've already done some work here, and we actually can study. We've already rotated our molecule. Flipped our molecule, so that for center C, our hydrogen's already in the back. So let's just draw what we see for center C. Okay, so we've drawn center C. Now let's assign our priority. So A, B, C, once again, which group gets the highest priority? A, B, or C? A, so we assign A as priority 1. What's the next highest priority? So now we count one carbon out since there's a tie. What's the next highest priority? B, yep. What's the next highest priority? Well, that's obvious. C. So then we count, and we count from highest to lowest priority. And as we see, we're moving clockwise. So we assign stereocenter C as the R configuration. Does this example make sense to everyone? Is everyone comfortable with that so far? Okay, perfect. So let's keep going. Let's tackle this complex example. So I'll allocate everyone about 5 minutes to work through this example, and then we'll resume in about 5 minutes. So build the model kit, and let's assign A, B, C, and D. So this will be the most complicated example we'll be working on today, and I'll be making the model kit during this time. But let's try and draw out and assign the configuration for each of these centers. And don't be shy to type in chat so I can provide some feedback. Oh, sorry. Yes, so everyone's pretty fast at these. Let's keep going and let's assign the rest of our centers. I'm seeing good progress so far. And this is exactly the kind of question you'd potentially see on an exam. So you should know how to handle these types of questions and assign the centers in relatively complicated molecules. Because if you can do something like this, then you can probably assign the stereochemistry and configuration at any molecule I come up with. So let's see if we have some assignments for centers C and D, and then we'll be ready to discuss. Okay, I see some students starting to assign the configuration at Stereocenter C. Keep up the good work. We're almost ready to discuss. Does anyone have a volunteered solution for the configuration at Stereocenter D? It's okay. Would anyone like to chime in for? Okay, so we have our first batch. C and D are a little bit tricky, but let's start first and foremost just by visualizing. Oops. And you know, I'm really getting a lesson in enantiomers because the camera system for this, it projects the mirror image. So I keep having to make the enantiomer in my model kit. Just thought it was a little bit funny to note. Okay, so here's what this molecule, oops. Okay, so here's what this molecule looks like as a 3D depiction. So let's start with the easy one. Let's start with center A. Let's start with center A. Now all we have to do is just rotate our center so that our hydrogen's pointing away from us, and then we draw what we see. Okay, so let's focus on center A now, and I'd like you to assign priority groups. So if we have A, B, C, which group gets the highest priority number? Group A, group B, or group C? Which group gets the highest priority number? A, B, or C? A, yep. What's the next highest? So if we compare our two carbons, which group gets the next highest priority? C, exactly right. And then finally B, we draw an arrow going from highest to lowest priority. So this is clockwise. So we assign this stereocenter as R. Does that make sense so far? Is everyone comfortable with that so far? Okay. So center B is a freebie. It's almost given away to us. The hydrogen's already in the back. So all we have to do is just draw what we see. Okay, now let's assign our priority groups. Let's assign our priority numbers. So for A, B, C, which group gets priority number 1? Which group gets priority 1? A, B, or C? Which group gets priority 1? Remember, we're focusing on the atom directly attached to our chiral center. So A gets priority 1. What's the next highest priority? C, yep. And B gets number 3 by default. We then draw an arrow from highest to lowest priority, and as we see, we have the R configuration. Does that make sense to everyone so far? Okay, let's focus on C and D now. Let's focus on C and D. So let's take a look at stereocenter C. So in the model, this would be this stereocenter right here. Our hydrogen's in front and our methyl's in the back. So we have to rotate our molecule. So I'm going to rotate my molecule. I'm going to flip it essentially 180 degrees. And now my methyl group is in front and my hydrogen's in the back. My methyl group's in front and my hydrogen's in the back. So now all I have to do is just draw what I see. Does everyone understand what I did? So we start off with the following structure. The hydrogen is pointing out of the page. We flip our entire molecule 180 degrees. Our hydrogen is now pointing into the page, and we draw just what we see. Okay, so now we're ready to discuss center C. And just keep in mind, a really cool 2-for-1. We've set it up so both of our hydrogens are now into the page. Okay, so assigning priority groups for center C. So let's do A, B, C. So which group gets the highest priority, A, B, or C? Which group gets the highest priority, A, B, or C? C, yep. So we're going to assign C as number 1. B gets number 2, and A gets number 3. So if we draw our arrow going from highest to lowest priority, we see we're moving counterclockwise. And counterclockwise, we assign that as S. Does that make sense to everyone? Okay, so let's look at our last center. Remember when I told you when we flip this molecule upside down, we also made it so the hydrogen at carbon D is in the back? Just as a refresher. This right here is the hydrogen attached to carbon D. We flip our molecule 180 and we get a bit of a 2-for-1. So now all we have to do is draw what we see for carbon D. And this is why I kept telling everyone, if there's one tool you have to get for organic chemistry, it's a model kit. Because doing all these rotations in your head, although possible, is not very fun, especially not on a test where you're under a time limit. Okay, so we have our center D, and now this is another study where we're going to have to be very careful with our priority assignment. So if we compare A, B, and C, which group gets the highest priority? Which group gets the highest priority? A, yep, A gets number 1. We count 1 carbon out. Which group gets the next highest priority? And don't get too distracted here. And let's get a few more pieces of input. Does anyone else have an opinion on this? Is it B or C? And let's be really careful about this. Very careful. B is the correct answer. Because attached to this carbon, we have a carbon, and 2 hydrogens. Attached to B, we have 3 carbons and a hydrogen. So B wins out. Does that make sense? Does that make sense to everyone? So now we draw our arrow, and as we see, we're moving counterclockwise. So we assign this center as S. Does that make sense to everyone? Is everyone comfortable with those assignments? Okay, so let's check. We'll stop here for today. Today is a good stopping point. Right here is a good stopping point, and we'll resume in lecture Monday.